Chapter 1 in this textbook, it's about structure and bonding. It is essentially review from General Chemistry 1, from your first semester of General Chemistry, is when most of you should have learned about at least a lot of these concepts at some level. So hopefully they sound familiar. If you're really having trouble keeping up with this chapter, I would go back to possibly to a general chemistry textbook and reread the sections on structures, on bonding, on shapes of molecules and things like that. And if you don't have access to one of those, you can come and talk to me. I can possibly let you borrow something. The libraries at the school have textbooks that you can refer to in their reference sections too. Also, if you'd be interested, I have lecture notes from when I taught General Chemistry 1 that I can make available to you if you like. So let me know if that's something you'd be interested in. Let's just start out in general why it is that we study organic chemistry. You're all in this course pretty much because it's a requirement for some sort of program that you'll be entering. A lot of you will be doing some sort of medicine or allied health or pharmacy or chiropractic, veterinary, things like that. All of those higher level professional medical careers require some level of organic chemistry. Mostly because of prescribing medications, anything like that requires a pretty good knowledge of the organic chemicals that make up those medications. Otherwise, fields like biology, ecology, environmental science, things like that require some knowledge of organic chemistry just because biology itself is applied organic chemistry. So having a knowledge of organic functional groups and how these molecules work will be really key to understanding how biochemistry happens, how the body's actual chemical functions work. So I say here that 99% of the known chemical compounds, and it's over 30 million of them, are organic compounds. So of all the compounds out there, organic compounds are pretty much all of it. Inorganic compounds make up a tiny minority of all of the actual compounds that are out there. So, take a look. Here's some common molecules that I'm sure all of you have heard of. Here's Vioxx, painkiller. Here's Viagra. Here's cholesterol, all things that we've heard of. These are all organic molecules. They have pretty complicated structures that look probably a bit confusing right now, but it won't be too long where we start recognizing patterns in these molecules and we can start to break them up and analyze their different portions and so on. So let's get a good definition down here. What is an organic compound? All organic compounds contain what? And before we answer that, let's just think for a second. It used to be that people thought that there was something fundamentally different about organic compounds and inorganic compounds, that there was some sort of magical vital force that organic compounds had that somehow allowed life to happen, that there was something fundamentally different about these organic compounds. But that idea got shot down pretty quickly when an inorganic compound, ammonium cyanate, it's inorganic, it was found that when you heat that, urea could be synthesized, and urea was a fairly commonly known organic compound. So because of that really shot some holes in this idea of something fundamentally different. It's just ammonium cyanate. It decomposes, it forms this organic compound on its own. There's nothing magical about it, nothing special. So urea, it is an organic compound. It's one that we would consider organic. The thing that all organic compounds have in common, therefore, is nothing about really where they come from or what they do or anything like that. It's just that they all contain carbon. So there are some inorganic compounds that contain carbon. Obviously, look at ammonium cyanate down here, NH4 plus OCN minus. There's a carbon in there, but those are in the minority, obviously. And it is true that all organic compounds do contain carbon. So if it's an organic compound, you can be assured that it contains carbon. So what's so special about carbon? Let's take a look at our periodic table here. Highlighted on this table are pretty much the only elements that we'll be dealing with in organic chemistry. So hydrogen, carbon, nitrogen, oxygen, fluorine. So most of them from the right-hand side of the first row. Then phosphorus, sulfur, chlorine, bromine, and iodine. That's about it. We're not going to talk a whole lot about transition metals. I think might be one or two that come up in a reaction or something at some point, but our discussion will be focused pretty squarely on carbon, but with some of these other common elements that are bonded to carbon. So carbon is in group 4A. On this periodic table, it's a number 4 and A, but a lot of times it is IV, Roman numeral, followed by the A. We're going to be most interested in these group numbers that have the A behind them. So going 1, 2, 3, 4, 5, 6, 7, 8 across the main group, skipping the transition elements there. So fourth group, essentially the fourth column of the main group, that means how many valence electrons does it have? Those group numbers are very handy to us because those are counting up the number of electrons in the outer shell. So carbon has 4 valence electrons. How many covalent bonds does carbon form? Well, let's look over at the noble gases here. All of these noble gases, at least starting with neon, argon, krypton, xenon, they have 8 valence electrons. That's a magic number that makes atoms stable. Carbon only has 4 valence electrons, so it needs 4 more. So it will actually bring in 1 valence electron from something else with every new covalent bond that is formed. So we'll draw some structures of these in a little bit, but it turns out that carbon forms 4 covalent bonds. It has its own 4, and we'll draw some more structures here in a little bit, but carbon has its own 4 valence electrons. So it would have to bring in, for instance, 4 hydrogens in order to pair with each of those, in order to make 4 covalent bonds. Since a covalent bond is a pair of electrons, we'll talk about that later. So carbon is unique in its ability to form chains with itself. So carbon can form very long chains. I can make this chain of 6 carbons like that. That's hexane, a very common solvent, but it's not just that. We can have chains of 20 or 100 or 1,000 or 10,000 carbons. So it's just because this carbon-carbon bond is very strong. Well, let's just say relatively strong. Whereas other elements, the bond between that atom and another atom of that same element isn't quite strong enough to hold up into a big chain. And for instance, something like silicon, that's right underneath carbon on the periodic table, the bond between silicon and oxygen is actually more strong than the bond between silicon and silicon. So if I were to have a chain of silicon atoms, it could be very easily oxidized. So the silicon-silicon bonds would break and we'd make bonds to oxygen because those are stronger. With carbon, that's not the case. Carbon-carbon bonds are actually stronger, so these chains don't actually get broken up by oxygens. Oxygens can bond to these individual carbons, but it's not a matter of breaking those chains up. So with our little more general definition of what organic is, that organic compounds just contain carbon, that means that we're not particular about where organics are from. Organic compounds can be formed by nature, usually called natural compounds or natural products. And nature is by far the most efficient synthesizer of organic compounds. Those 30 million compounds we referenced before, the vast majority of those, I think, have been synthesized by some factor in nature. And they can be extracted from plants and from animals and things like that. And oftentimes those substances go on to be the precursors for useful substances like medications and new materials and so on. So organic compounds can also be created in the laboratory. Those are usually called synthetic products. And the exact same compound can be formed by nature and formed in the laboratory, right? Because there's no special magical vital force. A synthetic compound can be identical in every way to a natural compound. That's very important to understand, and it's a common misconception that a lot of people have, that if something is natural, it is inherently safer or better for you or something, when still to this day, I believe some of the most powerful, potent poisons known to us have been synthesized by nature. So oftentimes a useful natural product can be isolated, and then scientists in the lab can go synthesize that from scratch in order to ramp up its production. So that could be very useful to in just the fact that you have to process 20 tons of sea sponges to get half a gram of the active ingredient you're looking for, whereas you could very efficiently synthesize it starting from simpler materials and using reactions to build it up.